There's Chicago, and he's going to tell us about quantum.
Yeah. Okay. Okay. So do I have to turn on the mic or it's already on? Already on. Yeah. Okay. So the title of my 3 lectures is Quantum Hole Liquid. This is a title that was given to me by the organizer, and there is no further instruction. And based on the theme of the workshops, I think that the organizers want me to give an introduction to part of quantum physics of strongly interacting quantum matter, to an audience whose interest is primarily in classical fluid dynamics and related topics. So preparing this it's impossible to compress the whole knowledge of theoretical knowledge of quantum hole physics in 3 lectures. So there is a lot of trade-off that we have to make. Some of the material that are pretty standard in any textbooks of any lecture notes or textbook of quantum hole physics, unfortunately, has to be dropped. But some more less known topics, which I still think are beautiful to learn about, will be presented. So in lecture 1, the end goal of this lecture 1, I think, will be, I'm going to try to explain the phenomenon called integer quantum Hall effect. Is my writing big enough? Okay. So by quantum Hall effect, we mean a set of physical phenomena that typically occurs under 3 conditions. First, we have to have 2 dimensions, 2 spatial dimensions. And sometime in the literature, time is taken as another dimension. So one talk about 2 + 1 dimensional system, 2-dimensional electron gas, 2-dimensional degenerate electron gas. Sometimes we talk about that. Then 0 temperature as typically required for quantum effect to appear. So we have to have 0 or almost 0 temperatures. And then we have to have high magnetic field. How high the magnetic field should be, then we are going to discuss later. And in experiment, typically it's the field of that measure in Tesla. Okay, so before talking about the quantum Hall effect, let's define some quantities that are measured experimentally. So we have so in experiments, we have a sample, 2-dimensional sample. Okay, and then the magnetic field is going to be perpendicular to the board. And then in experiment, one push a current through the sample, current called I, and then one measure the voltage difference here. Measure the voltage difference. We can measure the voltage difference also between this and this end. That would be the usual measurement. When there is a magnetic field, one can also measure the voltage difference between this and this. Okay, so let's recall some formula in electrodynamics. If we have an electric field, then there is a current that is generated by the electric field. So typically this formula is written as J equals sigma E. J is the density of current density, and sigma is called the conductivity. That formula works only when the system is isotropic and doesn't have a magnetic field. in general, sigma is a tensor. So we have to write sigma ij times E of j. In a two-dimensional system like ours, ij run x and y. So Ohm's law, and then we can reverse the Ohm's law, and sometimes we write E of I equal rho ij j of j, where rho is called the resistivity tensor, which is just the inverse of sigma. Nothing interesting in that. And then for an isotropic system, which in the real world is never, the crystal is never isotropic, but for our purpose, it's sufficient to assume isotropic. In fact, we don't need isotropy, we just need a sufficiently high crystal symmetry to require that sigma ij is equal some scalar times delta ij plus another quantity that I will call sigma h per whole times epsilon ij. Epsilon is plus minus 1. That is the only two rotationally invariant tensors that one can write in 2 dimensions. And so the formula for this J relationship between J and E becomes sigma L, sigma H minus sigma H, sigma L times Ex dy. So we will call this the whole conductivity. And this one is I call longitudinal, just usual conductivity, or L here, longitudinal in conductivity along the same direction as the direction of electric field. Now, in experiments, one measure not the current density, but the total current. Normally, one doesn't measure the electric field, though it's possible, but one measures the voltage difference. And so there is a version of this formula which refers to this integrated quantity. So, for example, the current, the total current for flowing along the x direction. Right. So here's the current. Let's set this direction to be x, this one to be y, and the size of the sample we are going to take it to be a rectangle with size Lx and Ly. The total current along the x direction is the current density integrated along this y direction. The total current is equal to Ly times J of x. And the current along the y direction is Lx times Jy. Any question? Should be obvious. And then the voltage drop along the x direction is the integral of the electric field along the x direction from this end to this end. And so it's Ex Ey times Ly. And you can put this in and relate the quantity, which is now more integrated version of this formula. Let me call that I. So I'm not sure if I have the formula for that. You will find that I of x equal, let me just write down the formula that we get at the end. Ly over Lx, E of x, plus there's missing sigma L, E of x. So I'm writing this formula, but for the total current and the total voltage, V of x plus sigma H, V of y. And similar formula for I of y that I'm not going to write down. One thing you've noticed here is that the geometric factor cancel. And so the whole conductance is the same as whole conductivity. There is no difference, while there is a geometric factor in the longitudinal part. So usually when we do measure the resistance, we have to then multiply it and divide it by the size of the rectangle to find the resistivity or conductivity. But here we don't have to do that for this off diagonal or the whole part. Similarly, one can define the resistance as the relationship between voltage. This is just the inverse of the formula that I've written here. And we see that the whole resistance is the same as the whole resistivity. In the off-diagonal part, there is no difference. That makes the task of measuring the conductivity, the whole resistivity, whole conductivity, much easier to do in experiment. But I'm not an experimentalist, but I imagine that this make the measurements much easier. Okay, so the first, I think not sure I know the history well, but I think the first person who measured the Hall effect is Hall, when he was still a graduate student. So he find the following relationship between the whole resistivity and the magnetic field. So he find it to be a linear relationship. This can be derived quite easily now, knowing very little about the microscopic physics of the system. So let's do the simplest model. Sometime in condensed matter physics, this model is called the Drude model. The Drude model directly gives us an explanation for the linear dependence of the whole resistance to the whole resistivity. So we imagine it's actually even simpler than the Drude model. We imagine just a liquid of electrons, some charged particles. Mentions just usual kind of liquid. Now you know that they can be liquid of electrons, or in some semiconductor it can be a liquid of hole, some liquid of charged particle, and with some density, charge density. Let's call some charge density rho. And then it moves with some velocity v. So in the experiment, we push that with velocity v, and so there is a current, electric current, equal rho times v. And this fluid moves with a constant velocity. And so that means that the total force acting on each volume element is equal to 0, or the total force acting on each particle average to 0. So there is a force, total force, acting on a unit volume, infinitesimal volume of the liquid. And how do we get that from? So if the system is in an electric field, then the force would, there is a Coulomb force, rho times E, times the volume. So I'm just factor out the volume. Rho times E, right? Rho V is the volume, and rho times it's a total force, let's call that force density. acting on a unit volume is rho times E. But then there is also another force that we have, which is the Lorentz force. Because this is a current, we have a current, and in the magnetic field, how would I say, there is a Lorentz force acting on this current, which is J cross B. Okay, and there is another force in a real material. The electron do not move forever. There are impurity in a metal, and that impurity slow down the motion. If we set up a motion of electrons in a metal, it will come to a stop very quickly because of basically a friction that this electron fluid experience when the electron collide with the impurities in the metal. And this is proportional to J. So it's some kind of a minus gamma J. We have to have a friction force, and this gamma is some friction coefficient. And that total has to be equal to 0. That is the essence of the model. Now we're going to explore the consequences of this model. Okay, so now let's assume J point along the direction of X. So X 0. In experiments, we push the current along one direction. And then we can right away see here that this term is defined, this is defined, so the electric field is completely defined. Let's see. Making, do I make something up? No, I make up things. If I don't, normally we don't know what is gamma, and so gamma is it's dependent on the material, and so the X component of Y of E is not easily found without knowing this gamma, but the Y component of E is completely determined. So we have rho EY, I think, minus JX. So B is along the Z direction, BZ. Instead of BZ, I'm just going to be B. B is 0, 0. B is equal to 0 because the current J doesn't have the Y component. So from that, we find that E of Y is simply equal to B divided by rho charge density times J of X. In other words, what we found here is that the whole conductivity, which is the same as the whole conductance, is equal to, I think, with the sign minus E divided by rho. And that's exactly what Hall found. In a given sample, the density of charge is fixed. So changing the magnetic field changes the whole resistance. The coefficient here doesn't depend on the number of impurities in the system. Doesn't depend much. It depends on the total charge density, though. This is usually the determination of the whole conductance usually is used to determine the sign of the charge carrier in a system. Can find whether the charge carrier are electrons or holes by just measuring this. whole coefficient.
UI is what set up by charges.
So charge has to flow.
I know, but in order to set up that like UI, don't you need some plus charges and bottom and top bound?
In order to set up a EY, yeah, you have, roughly speaking, or this charge doesn't have to be inside the sample, it can be outside. Yeah, it can be some gate that you put that is separated from the sample through a vacuum or an insulator. So the classical theory make a very well-defined prediction of a linear dependence of the whole resistance on the conductivity on the magnetic field. So that is the situation before the experiment that was done in 1980 by von Klitzing. So at that time, it becomes possible to make very clean sample and go to sufficiently low temperature and high magnetic field. And what von Klitzing found is a graph that looks like this. So I'm just drawing the maybe more modern version of the data. So here's RH, here's B. For low magnetic field, we find a linear dependence, but at some value, we start to see this zigzagging feature, which becomes more and more strange at higher magnetic field. Roughly speaking, what we find is the following. At high magnetic field, there is a region where the whole resistance doesn't change at all when we change the magnetic field. It comes to a constant, a flat constant in the graph, which are now called plateau. So one of these, each of these is a plateau. More interestingly, the value of the whole resistivity at these plateaus, they receive very well-defined values. So R of H at the plateau R of X, RH is equal to EH divided by E squared 1 over N, where N runs 1, 2, 3, etc. Integer. So this is something like, I forget, 26 kilo ohm, roughly speaking. So each of these plateaus correspond to a value of the resistance, which is the multiple 1 over integer times the combination of fundamental constant of nature. So H, again, is 2 pi H bar. So historically, it's just been defined reversely. And the what is also interesting is that if one plot the value of the longitudinal resistivity, at the plateau, longitudinal resistivity is basically 0. There's no longitudinal resistivity at any of this. And this longitudinal resistivity simply is non-zero only in the transition region between different plateaus. So this is RL. And this has been verified to be valid with accuracy, incredible accuracy, 10 to minus 9. An accuracy that's sufficient now for I think, to redefine the kilogram. Now, the kilogram is no longer tied to a physical kilogram in Paris, but is now defined through the value of the whole resistivity in the quantum Hall effect. So this is what happened in 1980, and a couple of years later, I think 1982, the fractional quantum Hall effect is found. That is showing Stormer. That in which the whole resistivity, the plateau, or even cleaner sample was found to come to the more complicated pattern of ratio of two numbers. So it's integer, and this one is also integer. Not all the fractions is realized as a plateau, but a lot of them. We are going to talk about maybe only one of these. So why there is this incredible quantization of the whole resistivity?
Good question. I don't think I've heard the word name Goddard.
Goddard? Yeah, the Nobel Prize was given to two Stormer and Laplin. Laplin, who is the, I think Goddard, I think he present. I'm not sure. Yeah, I think he the sample comes from him.
Okay.
Yeah. Yeah, yeah, but the Nobel Prize was given to Stormer and Laplin, who constructed the first theory explaining the fractional quantum Hall effect that at Q equal to 3, P equal to 1. What is the reason for this quantization? I hope to explain a little bit to you, at least in the case of the integer quantum Hall effect. Its explanation can be done rather in a way that makes that's quite convincing. And then the fractional quantum Hall effect is a bit more complicated, but the physics is very rich, and some part of this physics is connected to the theme of this school, hydrodynamics. Though, yeah, we will see. And then let me also put all this in a more modern point of view. From the modern point of view, now we the terminology that we use now is the following. We call this one is already written. We call the each of these quantum Hall plateau correspond to a quantum state of matter. So the terminology here is borrowed from the usual notion of state of matter, like solid and liquid. There are different state of matter that differ from each other by symmetry, or ferromagnets and paramagnets differ from each other by the symmetry. Here, the difference between the plateaus are not in the symmetries, but in some other properties that we know related to topology. So each of the plateaus is characterized by a different value of the whole resistivity, and the transition between these plateaus. So another thing to emphasize, to say, is that these are gaps. Sometimes we emphasize the thing that the state of matter are gap state of matter, and by gap state of matter, people have in mind the fact that the ground state in this quantum system, the ground state is separated from all the excited state by an energy gap. And that energy gap doesn't go to zero as the size of the system goes to infinity, while the difference in energy between different excited states goes to zero, and the system size goes to infinity. So this quantum gap state of matter and the transition between this quantum Hall plateau, this transition region, somewhere here the system becomes gapless. So these plateaus are different quantum state of matter. First of all, they have different Hall conductivity. And secondly, transition between them necessarily involve a point where the gap is zero. The system has no energy gap between the ground state and excited state. Okay, so that's basically the introduction. And now we are going to talk about the single particle dynamics and the integer quantum Hall effect. Any questions so far? Yes. So the experimental evidence for the gap, there are multiple. So first of all, the fact that RL is zero is not exact. So it's actually some function of temperature that behaves like E2 minus delta over T. That would remind you the activation formulas. Delta is the energy to activate a charge. That would correct some process that contribute to this. This is one information we get from the gap. So there are other information, for example, by doing Raman scattering, we can also find out that we can excite the system by shining photon and then observing photon that come back with slightly less energy. So there's another measurement, direct measurement of the gap. Yes, and another question?
Is there any relation between RL and RE? For this figure, it looks like RL seems to be equal to the unity of RE.
There is no, as far as I know, there is no as far as I know, this really seems to be true experimentally, but there is no theoretical understanding of why. Yeah. Any more questions? Okay, so if not, then let us go to a more systematic study of particles in a magnetic field. So at first, we want to remind ourselves what we know about one particle, a single particle. Dynamics in B field. And that will be the key for us to understand the integer quantum Hall effect. Okay, usually one can, the first thing one can do when we have a particle in magnetic field is to write down the equation of motion. So the equation of motion is like this. Particle, the acceleration is proportional to the force, which is E times V cross B. So X dot cross B. So that's the usual formula that we know from just electrodynamics. But I'm going to follow a slightly more complicated route. So I'm going to try to understand the Hamiltonian formulation of the problem of a particle in a magnetic field. So since that will be useful to introduce certain notion that we needed later. So a Hamiltonian of a particle in a magnetic field is also something that can be read from textbook. We have a kinetic term, 1/2m p squared, but instead of p squared, we write the following: p minus e a x square, and then we have plus e phi X. So the second term is the potential energy of a charged particle in a scalar potential. And this one is a vector potential, and the B is curve A. And the dynamics of the system is governed by the Hamiltonian equations, which can be checked. This equation can be checked to be equivalent to a set of Hamiltonian equation, which is usually written as x dot equal dh over dp, and p dot equal minus dh over dx. Again, because I'm a theorist, I'm going to make things a little bit more complicated, but more flexible at the end. We are going to introduce the Poisson bracket. Also something very well known in classical mechanics. The Poisson bracket is defined so that the Poisson bracket of x is the same as Poisson bracket between two different y is 0, and xy pj is equal delta ij. Unfortunately, Landau defined it with a sign that differs from almost everybody else, but I well follow this non-Landau Lifshitz notation. So x, so anything dot is equal to its Poisson bracket with the Hamiltonian. So that allows us to write the time evolution of any quantity as its Poisson bracket with the Hamiltonian. Okay, so now I'm going to give an alternative Hamiltonian description. I'm going to write the Hamiltonian in the following way. I'm going to define K x, where K is P minus EA. So I think the terminology in literature, this K is sometimes called the kinematic momentum. To distinguish it from P, which is the canonical momentum, the momentum that is canonically conjugate to the coordinate x. So the kinematic momentum is nothing but just m x dot, right? The equations, one of the equation of motion is that I think x dot is equal to this thing divided by m. So in this formulation, we would have the Poisson bracket between x is 0. The Poisson bracket between x and p, x and k would be delta ij, because the phi does not have phi commute 0 Poisson bracket with x, but the Poisson brackets of k I and kj is now non-zero because k contain both p and x, and then when you do Poisson brackets between two functions, let's say f and g, you have to do df over dx and df dg over dp J minus the same with the role of F and J exchange. And so you do the calculation, you find that the bottom bracket of K no longer commute. So when I say commute, I have in mind the quantum version of this Poisson bracket, which is the commutator. So they have non-zero Poisson bracket, which is equal to E times Fij. So Fij, Diij. So in our two-dimensional system, this is just E times epsilon ij times the magnetic field. So this is a new Poisson bracket that sometimes is also useful. So this Poisson bracket with the Hamiltonian define the dynamics, the full dynamics. And this kinematic momentum is also useful because it's gauge invariant. Does not depend on the choice of the gauge, which can be seen because it is just a physical velocity of a particle. So velocity as a physical quantity. So kinematic momentum is gauge invariant. Doesn't depend on the gauge. Okay, any question so far?
What is sum over I and J?
Yeah, there is a sum over I. So it must be repeated, yeah, index. And by the way, once we have this, we can compute any Poisson bracket within any function of x and k. So f of x, k, commutator with the g of x and k would be equal to something very similar to this one, xi dg over dt k I minus same as f j. But now there is an extra e b epsilon ij df over dki dg over dkj. So the Poisson bracket can still be defined. It's just more complicated than previously we have.
You're doing everything classically. You eventually have to go and make anything to.
I'm going to avoid quantum mechanics as far as we can do. We actually can do a lot with without ever solving the Schrodinger equation. Harmonic oscillate can be quantized by Bohr-Sommerfeld. So I'm going to try to appeal to Bohr-Sommerfeld type of argument. Of course, everything can be done more rigorously by solving the Schrodinger equation. Okay, so that is what in formulas we have. But now let's try to let me so how a particle would move in a magnetic field. So this is a very simple thing one can get by solving the equation. Okay, so now x, let's write the equation. X dot is equal to some brackets of h and h, but there is only k square over m, so this is ki divided by m. And then k dot KIH. So now let's first set the scalar potential to 0. Just purely particle in a magnetic field without any electric field. No electric field. And so this one is just commutator of Ki with this k square over 2m. Because k and k do not commute, this is non-zero. And by computing this following our rule, find that is EB over M times epsilon ij kj. Yeah.
I think the answer is variable x, x, k. They are not canonical variables.
They are not canonical. X and P are canonically conjugate with each other, but now X and K are not, because K and K, commutator of K and K is non-zero. So in some sense, if we want to quantize this system, it's easier to do it in terms of X and P, because P is now would be derivative with respect to X.
Since they are not canonical,
Why it's satisfied what? It doesn't need, the variable don't need to be canonically conjugate. You can, if you have a Poisson bracket, then any the time derivative of any variable is just a Poisson bracket of that variable with the Hamiltonian. That's it. Yeah. It doesn't depend on how you. It doesn't need the canonically. This equation are just equivalent. One can show the equivalent to the previous one. Okay, so what will happen here is that the particle is going to move. Our particle is going to move in circular orbit. So this K, if I draw a trajectory in K space, this one is going to be just motion like this. There is a very unfortunate choice that was made early in the history of physics, that the charge of the electron is -1. So I'm going to compensate that by choosing the magnetic field to be in the opposite direction. So that EB is, that always in my formula, EB is usually E and B comes together. So EB is positive. So I don't have to worry about the sign of E, sign of B. So then in K space, the particle move in a certain orbit like this. And in X space, then I'm not going to write down the formula, but you can easily find it by solving the equation. The particle move in also circular orbit around some center. Like this, and the frequency of the motion is EB over M. That is called a cyclotron frequency. Again, something very well known in physics. Okay, so now I'm going to define the following thing. So-called, going to introduce some variables that are normally called the guiding center coordinate. Am I going too fast or too slow? Okay. So the coordinates, the variables that we are going to see justify the name of guiding are defined like this. So let me write down the formula first. Ri equal xi plus 1 over EB times epsilon ij kj. Why these are interesting coordinates? And that because of the following properties that you can check very easily. That R and K has 0 Poisson brackets. They commute. This X, the commutator of X with this K, completely cancelled by the commutator of K with K. This formula, the coefficient in front here has been chosen just to make that possible, to make that 0, commutator 0. So if this R commute with K, one thing we can say right away that if our Hamiltonian is just a function of K, like our K square over 2m, then R dot is to be equal to 0. This linear combination is unchanged under the time evolution. Okay, so physically what that is in that figure over there. Let me just move it down and then move it up again. So this R basically is just the coordinate of the center of the trajectory of a particle. X changes periodically in time, K changes periodically in time, but the linear combination between them in that particular linear combination, the time dependence completely cancel out, and we have with the center of this orbit. So the center of the orbit, so it's called guiding center, and it stay in one place if the magnetic field is the only thing that we have. Okay, so that's pretty simple story. But what we lose is that this R no longer commute with themselves. The coordinate X used to be to have 0 Poisson brackets, and now R and R, you can check, can compute this R and R, they have non-zero Poisson brackets with each other. It's equal to minus epsilon ij divided by EB. That's I leave that as an exercise. Okay, so this allows us to solve the introduction of the guiding center coordinate, allows us to solve an interesting physical problem. That is the problem of the motion of a particle in an electric and magnetic field turning on at the same time. So let us reintroduce into the system the scalar potential. So here my Hamiltonian becomes K square over 2m plus scalar potential, that is E phi of x. So I think the electric field is the gradient of phi. So now it's non-zero. Okay, so now I'm going to solve the problem of motion of particle in phi field, assuming that this phi is sufficiently smooth. So for the precise definition of that is the following. Suppose we are looking at motions that correspond to a given energy. So let's assume there is some energy E. When we have an energy E, then this K, typical value of K, since the energy is mostly the kinetic energy, K is going to be square root of ME. Square root of ME, okay? And now I'm going to make the approximation. That I can replace 5x can be replaced by phi of R. So when that can be done? That can be done if phi is sufficiently smooth function. So phi varies very slowly. It's a function of x. So slowly that the difference between R and X can be neglected. That is the scale of the difference between phi and X, which is 1 over EB times K, which is what? Square root of ME, is small compared to the length scale at which my potential phi changes, much smaller than this length scale L. In other words, I'm going to look at the change at the potential which changes under length scale, which is much larger than the radius of my orbit. So the circular orbit has some radius, and I assume that the potential changes slowly at the scale of that radius. Then if that can be done, then the problem becomes very simple. If I can replace that by R, right, then the equation of motion becomes simple. So first of all, the equation of motion for K remain the same. K dot is equal, because K and R commute with each other, right? And so K dot is governed by the same equation as it was before for free system, so that K is a periodic function. Basically, K like this rotation before. And R dot now, what is R dot? R dot, to compute R dot, I have to compute the commutator of R with H. But now R with K squared, there is no, this commutator is 0. So Ri dot is equal to 0 plus E times Ri phi of R. And now we remember that the commutator of the Poisson brackets between two R are non-zero. So that give us the following, give us minus 1 over EB times epsilon I d phi over d and E cancel, so just 1 over B epsilon ij over R J. So the motion of our particle in this approximation becomes decomposed into two different motions, superimposed onto each other. One is the K, and the other is the motion of the guiding center. Physically, that is what happened is the following. Happen is that we have circular orbit. So this X still have a motion periodic in space, but the center of this orbit slowly drifts in time. So that motion here is determined by the second equation, right? And the guiding center move along the lines where the potential phi of r is equal to constant. It moves along the direction that is perpendicular to the gradient of phi. That means it moves along the direction where the function phi is constant. So move along the equal potential curve. That's how the motion in a very high magnetic field. The motion of a particle at this form. Any question so far? Yeah. So here I'm doing classical theory. In a classical theory, everything is very simple. But you're asking why it is so simple, or? So I haven't do quantum theory yet, but yeah, the quantum. I want to have a shortcut to quantum theory, and so that's one way to do that. We are going to, yeah, because the quantum Hall effect is basically a quantum, yeah, system. Yeah, it's just to introduce this. All these notions are going to be they actually have equivalence in quantum theory. Just imagine this P is replaced by operator, and then the Poisson commutators, and then a lot of these are going to be so let me try to get to, actually we can get to the integral quantum Hall effect by doing basically semi-classical quantization of particle in magnetic field without even trying to solve any Schrodinger equation. So that's probably what we're going to do. Okay, so the quantum mechanics of a particle in a magnetic field was first considered by Landau in 1930. Landau found the eigenvalues of a single particle in a magnetic field. So we are going to reproduce what Landau found by appealing to this semi-classical picture. Okay, so now I have to do the following thing. All we need to do is to find the energy eigenvalues. So again, we set phi equal to 0, and the Hamiltonian is simply k squared over 2m. And one thing that we have is that kx and ky do not commute. Kx and ky commute to the commutator is EB. So they in some sense, these can be thought of as creation and as momentum and coordinates. It's like x, some x and p is equal to 1 in the usual one-dimensional quantum mechanics. So this basically is, if I think about that, it's kx squared over 2m plus ky squared over 2m. If I identify kx with x and ky with p, one would be p squared, the other would be x squared, would be a harmonic potential, harmonic oscillator. And then from that, we find all the energy eigenstate. So the result is the energy is h bar time omega n plus 1/2, where if you do this calculation, for example, you can just say set this x to be kx and p to be ky divided by eb, and then do the mapping and find the omega. And the omega here is simply equal to the cyclotron frequency. It corresponds to what we expect in quantization. The oscillation frequency becomes the spacing between energy level. So these are called Landau level. But here we are missing one set of variables. The Hamiltonian commute with Ri, right, is equal to 0. So in the quantum theory, you can think about this as the commutator of H and R is equal to 0. So we have to have the, so that means that the ground state is degenerate, because we have, we can act on the ground state in the operator that we construct from this R on the ground state and get another state, we have the same energy. So we are going to try to find the degeneracy of this, how degenerate is each of the energy states. So that is also another thing that Landau found in his treatment of the in his quantum treatment of the particle in the magnetic field. Let's again do our shortcut. Which is also useful in developing the intuition of this problem. Basically, here we have this coordinate. We have the coordinates r, x, and ry. Where the energy does not depend on r, it depends only on k. So physically, in the classical theory, the energy of this motion is the same as the energy of this motion, is the same as energy of this motion. If all of this circle has the same radii, has the same radius, the energy of all of this trajectory correspond to all of this trajectory is the same. Right? In quantum theory, they would correspond to different, there will be a different quantum state that have the same energy. So this coordinate Rx and Ry, we have the same energy H. And we need to count the number of states in classical by doing basically a semi-classical procedure in the following way. Remember that Rx and Ry, the Poisson bracket between them is not equal to 0, but equal -1/EB. So again, these X and Y, they are like pair of canonically conjugate variable. If I think about Rx as P, and then this Ry should be thought of as X divided by EB. And then the Poisson bracket would be -1/EB. But we know a rule to count the number of quantum state. The number of quantum state is equal to integral of dp dx divided by 2 pi h bar. Each volume in phase space corresponds to a certain number of quantum state, which is proportional to the area of this volume. So this number of quantum state then translated into integral over drx dry. But now the proportionality coefficient becomes, if I'm not mistaken, EB divided by 2 pi h bar. That means that if we have a finite system with a finite size in X and Y, they are Ly and Lx. In this system, the number, each of these Landau level has a degeneracy that is equal to this integral, but the range of the integration over Rx and Y is limited by the size of our system. So degeneracy is equal to Lx, Ly, and EB divided by 2 pi h bar. This calculation can be done more. If you look at the quantum mechanics textbook, there is various ways one can get the same formula. One way I will not sure if this is the space. There is a space to do that, but let me write down this as a homework problem. So homework problem. So we know that in the symmetric gauge. So this homework problem is completely quantum mechanical. So in its symmetric gauge, that is a x equal -2 ey, ay equal dx. The state on lowest Landau level, that is n equal to 0, Landau level has wave functions, which can be written like this. With LB square defined as h bar divided by EB. So magnetic length. Put a system on a disk. Circular disk. Imagine that our system in the disk of radius. How many quantum state can you put inside this disk? How many quantum state fits inside this disk, and whether the number is the same as the number that we have found using semi-classical calculation about. Okay, so now we have like a little less than 15 minutes. I'm going to tell you how one can understand the integer quantum Hall effect. That's going to be this was the goal that we set up. So the integer quantum Hall effect can be understood simply as the result of the quantization of the energy of single particle in a magnetic field. So here we don't have to think about how these particles interact with each other. Let's assume that the interaction can be neglected. So these particles, each of these particles can be in one of the energy Landau energy level. Electrons are fermions, and so they when one state is occupied, the state cannot be occupied twice. So you can imagine a situation in which each of these states on a Landau level is occupied. So there is some degeneracy at each state, and we have imagine a situation in which all the states below this field and Landau levels, and all these are empty. So let's consider this situation first. So what is then the density of electrons, the number of electrons? So the density of electrons, electron density, is the number of electrons divided by the area. So the degeneracy is L, each of the Landau level has Lx times Ly, E B over 2 pi h bar. And then there is n of this level, but then we have to divide by the volume, two-dimensional volume, Lx and Ny. And so the density of electrons is n times Eb over 2 pi h bar. That's the density of electron. And now we can compute the charge density. Just E, each of electron carry charge E. And so that is n E square over 2 pi h bar times B. And remember the whole formula. Whole formula saying that the whole resistivity is B divided by rho, but then we can say that the whole conductivity is rho divided by B, which is N times E squared over 2 pi H, which is exactly the values that was found in experiment with integer quantum Hall effect. And so clearly the integer quantum Hall effect has something to do with the quantization of the eigen of the energy of the electrons in magnetic field. Okay, the values that we obtain here are precisely what was observed. Now, actually, this is not the full explanation, because in experiment we also see the following. We see the plateau. It's not only one. Here it seems that we have to fine-tune the number of electrons to be precisely equal to the number of state on each Landau level times an integer for that effect, quantum Hall effect, to be valid. But that's not the case in the real experiment when we change the magnetic field continuously. When we change the magnetic field continuously, the ratio of the density of electron, the number of electrons over the number of state on a level, can be fractional. It doesn't have to be integer. So how do we explain that for a range of magnetic field, the extra electrons or the missing extra electron do not contribute to the measured Hall effect? And here the explanation can be done in the following, using the following picture. Here we have to take into account the disorder in the system, and this disorder perturbs the Hamiltonian, and let's assume a simple model of disorder, which is just some random potential. So let's assume that the electron is random phi of x created by this disorder. We have to imagine this picture to be in 2 dimensions. So here I'm drawing the phi of x, but actually phi is a function of x and y. Okay, so now phi, let's also make the next assumption that this phi is very smooth. Smooth phi, that means that the semi-classical trajectory of these particles they follow the line of constant phi. Okay, so as we have seen in the classical approximation, the particle make this motion, but the center, the guiding center, the center of this orbit moves slowly along the line of constant phi. So what's happened now? If we try to solve this problem, then what happened here? You'll see that this Landau level is no longer completely degenerate. There is a variation of energy between different states in this Landau level, because the particle can be near the tip of here, the semi-classical picture, the particle can move here or here. They have slightly different energy. But imagine that we fill some certain number of Landau level, and then we put in some extra electron. One extra electron where it wants to sit. It wants to sit at some minimum. So when it sits near the minimum here, its orbit is going to be confined. We imagine like a landscape of potential. Near the minimum, the potential is concave. The electron move along the constant V line, and this constant V line is going to be a closed orbit. So if I draw a 2-dimensional picture, if I change the magnetic field so that there is one extra electron above the field Landau level, that electron is going to try to find the minimum of the potential and move around it. The next one is going to be moving in the next orbit. And the next one, maybe it will feel another minimum and move. But none of these contribute to the transport. The orbits basically close. And so what happened is that if I change the number of electrons, then until certain moment, all the orbits of these electrons are closed until some moment where there is orbits that are not closed. So the problem basically is a problem of percolation, that is filling up a random landscape with water, and see when the water we can go when water can, the surface of water stretch from one end of the sample to another end. So that's the explanation why we have such a stability of the whole conductivity, even away from the ideal situation of the electron filling up integer number of Landau level. So that's how we can understand integer quantum Hall effect. Next time we're going to discuss a more complicated, more interesting situation of the fractional quantum Hall effect. Any questions? Yeah. The picture of closed. This is a little bit subtle because here it's actually the transition here is driven by the disordered, and so I think the equivalent here is that the existence of this infinite orbit is the equivalence of the existence of the gapless state. So here is the states that are not localized, but unlocalized states that are not localized. So the situation, well, I think maybe I'm not, my understanding is not I haven't thought about that deep enough, but I think the situation is slightly different from the situation in a clean system when you actually close the gap. So here actually the transition between different Landau level is driven by the impurities. I have to think. Yeah. No, I have to. It's a gap between the Landau. Well, I think it's here still. There is a gap, which is the gap between the Fermi energy and the energy of the delocalized state. And so there is certain energy levels that correspond to delocalized state. And if your Fermi energy is below that, then you need the temperature, which is proportional to the distance between that energy and the energy. I can explain to you. It's like, sorry. I'm thinking about the one way of defining the gap is by measuring the exponential dependence of the longitudinal conductivity as a function of temperature. And in this case, what is measured is the difference between the Fermi energy and the energy of the delocalized state. And that plays the role of the gap. The transition between the Landau, between two quantum Hall plateau happened through the vanishing of that gap.
So early in the school, we heard from Antoine Benai, who talked about topological origin of some fluid lanes and invoked bulk interface correspondence. Can you push this semi-classical description, maybe through ray tracing, to connect with the Dallas quantization formula, the Chern number? Is it possible to push this a little bit further to make contact with those topological arguments?
I don't know. Yeah, it's yeah, but it would be something that would be nice to do. Yeah.
So I guess I just don't really understand the math part it's older. So you just going to add this random potential in the sorry, could you please explain the math part?
So when we put in the potential, we start to have a non-degenerate Landau level. So instead of a picture of all the state on the Landau level having the same energy, you can imagine that there is a certain band in energy. Each of these Landau level becomes broadened, and the width of this level is proportional to the width of the variation of the potential. So imagine now what I'm imagining is that I'm filling up, for example, one Landau level and try to fill the next one. So I decrease the magnetic field and suddenly one electron jump into here. So what does it correspond to? It corresponds to a electron making a small orbit near the minimum. Okay, so it moved along the curve of constant V near the minimum, and this is here. So once this electron is set in this trajectory, I cannot move it away. If I turn on some electric field, it will stay in one place, will not move. So it doesn't contribute to any current. Yeah. It corresponds to an energy level that's around here in the middle of the band. If the energy level that we put is too high, then the electron again should be moving around the maximum of the potential. So there is a equal height, another equal height. This corresponds to the bottom of the valley. This corresponds to the top of the mountain. And if you look at this map, usually you can find a line that goes in the valley between the maximum and the minimum and stretch from one end to the other. Yeah, they have to exist.
So when the correlation length of the potential smaller than the cyclotron value, then we can no longer use the semi-classical.
We can no longer use a semi-classical picture. Yeah, there is a certain rigidity of the quantum Hall effect that persists at least until the correlation length here is of the same order of magnitude as the magnetic because it's a qualitative effect, right? The qualitative effect has to suddenly disappear, so it cannot smoothly goes away. So this effect that we're describing here, the constancy of the plateau, they persist until certain until certain amplitude of the potential and certain correlation length.
But we increase the amplitude of the correlation length, through the polyvector until the limit of the correlation length.
I think what's important is the width of this span. It have to be smaller than the distance between them. But when you have that, I think the state in the bottom will always be localized in a magnetic field.
Yeah, so I understand some particles, some electrons are localized and they don't contribute to the dipole effect. So how do you relate this to the formation of particles?
So in the experiment, it is easier to imagine a situation slightly different from what's done. In experiment, we fix the number of electrons and change the magnetic field. But we can imagine fixing the magnetic field and changing the number of electrons. So the two effects is similar. When you change the number of electrons, first we fill certain number of Landau levels, so that contributes sigma equal like E square over 2 pi h bar. And then the next few electrons here contribute nothing. Yeah. How justified? How does topology enter the picture? So here's there are two different ways one can relate this to topology, and none of this is obvious at this level of the discussion. So one is with what Brad mentioned, one can express one is the Staulis KNN formula that relates the whole conductivity with certain integral of the Berry curvature of the wave function in Brillouin zone. That is not, I'm not sure how, again, this is Brad's question, and I'm not sure how to relate that to this discussion. Another way to see the emergence of topology is through the Chern-Simons field theory. Yeah.
Why don't we leave that for?
Yeah.